What if everything you thought you knew about the universe was just the tip of the cosmic iceberg? Picture this: somewhere out there, beyond the stars we see, space itself is stretching, twisting, and even rippling in ways that defy common sense. Time doesn't always flow forward like we expect. Matter behaves differently when no one's looking, and the very fabric of reality might be woven from threads we can't even see. This isn't science fiction. This is modern cosmology, the frontier of human understanding, where the biggest questions about space-time are finally starting to get answers. Think about the last time you looked up at the night sky and felt that humbling sense of wonder. That feeling is more than just awe. It's a glimpse into a puzzle that has captivated scientists and philosophers for centuries. How does the universe really work? What lies beyond the edge of our perception? Today, we're going to unravel some of the most astonishing theories that are reshaping our cosmic perspective. From the eerie influence of dark energy to the mind-bending nature of quantum foam, we'll explore ideas so profound they challenge the very definition of reality. This journey isn't just for astrophysicists or mathematicians. It's for anyone who's ever wondered how the pieces of our universe fit together. Whether you're a lifelong space enthusiast or someone who's just starting to dip their toes into the mysteries of the cosmos, what you're about to discover will stretch your imagination in ways you never thought possible. So buckle up, because by the time we're done, the way you see the night sky will never be the same. The universe is far stranger, far more intricate, and far more breathtaking than we've ever dared to imagine. And it's time to pull back the curtain. Einstein's vision of space-time as a flexible, dynamic fabric was nothing short of revolutionary. But what if even that groundbreaking idea is just the beginning? Imagine space-time not as a smooth, unbroken sheet, but as something far more intricate, like a cosmic tapestry stitched together from countless tiny threads. That's exactly where modern cosmology is taking us. While Einstein showed us that gravity bends space and time, today's theorists are asking an even wilder question. Does space-time itself have a deeper structure, something more fundamental beneath the surface? One of the most compelling theories challenging our classic view is loop quantum gravity. Picture the universe not as a continuous expanse but as a network of minuscule, indivisible chunks, like pixels on a screen, but encoding the very fabric of reality. These atoms of space could explain why we hit a wall when trying to reconcile Einstein's relativity with the bizarre rules of quantum mechanics. It's as if the smooth, predictable universe we thought we knew is actually built from a seething quantum foam at the tiniest scales. Then there's the holographic principle, a concept so radical it turns our understanding of dimensions upside down. What if everything we experience, every star, every galaxy, even our own thoughts, is actually a projection from a two-dimensional surface at the edge of the cosmos? It sounds like science fiction, but this idea emerges from the math of black holes, where information seems to be encoded on their boundaries rather than lost within. And let's not forget the multiverse. If space-time isn't fundamental but instead emerges from something deeper, could there be countless other universes bubbling into existence, each with its own unique laws of physics? The implications are staggering. We might be living in just one pocket of an endless cosmic landscape, where the constants of nature, like the strength of gravity or the mass of an electron, are set by random chance rather than necessity. All these theories share one thing in common. They push Einstein's legacy to its limits, daring us to rethink not just how space and time behave, but what they truly are. The closer we look, the more the universe refuses to fit into neat categories. And that's where the real mystery begins, because if space-time isn't the bedrock of reality, what is? The answer might lie in the next great clash of ideas, where quantum mechanics and relativity finally collide. At the heart of modern physics lies a paradox so deep it keeps scientists awake at night: quantum mechanics and general relativity, our most successful theories of reality, refuse to speak the same language. On one hand, Einstein's relativity describes space-time as a majestic, smooth fabric, warping gracefully under the weight of stars and galaxies. On the other, quantum mechanics reveals a chaotic subatomic world where particles pop in and out of existence, where certainty dissolves into probability, and where space itself might be pixelated at the tiniest scales. This isn't just a minor disagreement, it's a fundamental clash that fractures our understanding of the universe. Take black holes, for example. According to relativity, anything that crosses a black hole's event horizon is lost forever, crushed into a singularity where space and time cease to have meaning. But quantum mechanics insists that information can never truly disappear. So what happens when a particle falls into a black hole? Does it vanish, or is its information somehow preserved on the surface, like a cosmic hologram? This puzzle, known as the black hole information paradox, has been raging for decades, with luminaries like Stephen Hawking and Leonard Susskind taking opposite sides. The stakes couldn't be higher. If we can't reconcile these two theories here at the edge of a black hole, how can we trust them anywhere else? Then there's the measurement problem in quantum mechanics, where particles exist in multiple states at once until we observe them, forcing them to choose a reality. But how does this jibe with relativity's insistence that space-time is a continuous, objective stage where events unfold predictably? If quantum behavior depends on observation, whose observation counts? An astronaut near a black hole might measure a particle's properties differently from someone far away, thanks to time dilation. So which measurement is real? The quest to bridge this divide has spawned some of the most daring ideas in science. String theory proposes that the fundamental building blocks of reality aren't particles at all, but tiny, vibrating strings, threads so small they weave together the fabric of space-time itself. Loop quantum gravity, meanwhile, suggests space is made of discrete, interlocking loops, like a cosmic chainmail. And some theorists speculate that space-time might not be fundamental at all, but an emergent property of something deeper, like how temperature emerges from the motion of atoms. What makes this clash so thrilling is that it's not just a technical problem, it's a philosophical one. Are we missing a hidden layer of reality, a set of rules that unites the quantum and cosmic realms? Or is our very notion of space and time flawed, like trying to describe the internet using the language of steam engines? Every time we think we're close to an answer, the universe throws us another curveball. But that's the beauty of it, because somewhere in this great cosmic clash, the next revolution in physics is waiting to be discovered. Imagine an architect who builds entire cities without ever being seen, leaving behind only the fingerprints of their work. That's dark matter in a nutshell. We can't see it, touch it, or interact with it in any way we're familiar with, yet its gravitational grip is so powerful it holds galaxies together like invisible glue. Without it, the Milky Way would fly apart, and the cosmic web of galaxies we observe simply wouldn't exist. This mysterious substance makes up roughly 27% of the universe, 5 times more than all the ordinary matter we know. And yet, after decades of searching, we still don't know what it actually is. So how do we even know dark matter exists? The clues are written in the motions of stars and galaxies. Back in the 1930s, astronomer Fritz Zwicky noticed something strange. Galaxies in distant clusters were moving so fast that the visible matter holding them together shouldn't have been enough to keep them from escaping. It was as if an unseen force was anchoring them in place. Decades later, Vera Rubin found the same anomaly in individual galaxies, where stars on the outer edges were orbiting just as fast as those near the center, defying the laws of gravity as we understood them. The only explanation, an enormous halo of invisible matter exerting its pull from the shadows. The hunt for dark matter's identity has led scientists down some fascinating paths. One leading candidate is WIMP, weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and barely interact with normal matter except through gravity. Experiments like those deep underground in the Sudbury Neutrino Observatory or at CERN Large Hadron Collider have spent years searching for even the faintest trace of them. Then there are actions ultra-light particles that could theoretically permeate space like a cosmic fog. Some detectors use powerful magnetic fields to try and coax them into revealing themselves. But what if dark matter isn't a particle at all? Some theorists suggest it could be primordial black holes, remnants from the Big Bang lurking unseen in the voids between stars. Others propose modifications to gravity itself, like modified Newtonian dynamics, or MUND, which tweaks the equations to explain galactic motions without invoking invisible matter. Yet these alternatives struggle to explain all the evidence, like the way dark matter bends light around galaxy clusters in a phenomenon called gravitational lensing. The stakes couldn't be higher. Unlocking dark matter wouldn't just solve a cosmic mystery, it could open doors to entirely new realms of physics. Some theories suggest dark matter might interact with itself through unknown forces, forming hidden dark atoms or even dark stars. Others speculate it could be connected to the equally perplexing dark energy, the force accelerating the universe's expansion. One thing's certain: the moment we detect it, the universe will suddenly make a lot more sense, and yet, in true cosmic fashion, it'll probably leave us with even bigger questions. Until then, the search continues, with every experiment bringing us one step closer to unmasking the invisible architect of the cosmos. If dark matter is the invisible scaffold holding galaxies together, dark energy is the mysterious force ripping the cosmos apart at the seams. In the late 1990s, astronomers made a discovery so shocking it upended everything we thought we knew about the universe's fate. By observing distant supernova, they found that the expansion of the universe wasn't slowing down, as gravity would predict. It was accelerating. Something was actively pushing space itself apart, and that something earned a name as enigmatic as its behavior: dark energy. Today, dark energy accounts for a staggering 68% of the universe's total energy. Unlike gravity, which pulls matter together, dark energy exerts a kind of anti-gravity, stretching the fabric of space-time faster and faster over time. But what exactly is it? Einstein once proposed a cosmological constant, a static energy woven into space itself, to explain why the universe didn't collapse under gravity. He later called it his greatest blunder, but modern observations suggest he might have been onto something. Could dark energy be this constant and unchanging background hum of the cosmos? Or is it something far stranger? Some theorists argue dark energy isn't constant at all but a dynamic field, like an invisible cosmic weather system shifting over eons. Others propose it's a sign that Einstein's gravity needs revising on the largest scales, a tweak to the rules that govern the universe itself. Then there's the spine-chilling possibility that dark energy is just the first hint of something even more profound, a shadowy layer of physics we haven't yet glimpsed. To untangle this mystery, scientists are turning to next-generation telescopes like the James Webb Space Telescope and the Euclid mission. By mapping how galaxies cluster and how light bends across billions of years, these instruments act as cosmic time machines, revealing how dark energy's influence has changed or remained stubbornly consistent across the ages. The stakes couldn't be higher. If dark energy strengthens over time, it could lead to a big rip where even atoms are torn apart in a final, violent expansion. If it weakens, the universe might coast endlessly toward cold, silent dissipation. Yet the most tantalizing question isn't just about how the universe ends, it's about how much we still don't understand. Dark energy challenges us to rethink not just the fate of the cosmos, but the very nature of reality. Is it a fundamental property of space, a fleeting phase of cosmic evolution, or a clue pointing toward physics beyond our wildest theories? Every observation, every calculation brings us closer to an answer that could rewrite the story of everything. And in that search, we're not just uncovering the universe's secrets, we're discovering how little we truly know. Black holes aren't just cosmic vacuum cleaners, they're the ultimate test beds for physics, places where the universe cranks its rules to the extreme. Picture the event horizon, the point of no return, where gravity's grip is so fierce that not even light can escape. But what happens beyond that boundary? According to Einstein's general relativity, space and time swap roles. Falling inward, you'd find every possible path leads to the singularity, a point of infinite density where the laws of physics as we know them simply stop. Yet quantum mechanics tells a different story, one where information can't just vanish. This clash of ideas has sparked some of the most heated debates in modern science. Take Hawking radiation, Stephen Hawking's revolutionary idea that black holes aren't entirely black. Quantum fluctuations near the event horizon can create particle-antiparticle pairs. If one falls in while the other escapes, the black hole slowly loses mass, evaporating over eons. This means black holes have a temperature, a lifespan, and eventually a dramatic end. But here's the catch. If a black hole evaporates, what happens to all the information it swallowed? Does it vanish, violating quantum mechanics, or is it somehow encoded in the radiation? This puzzle, known as the black hole information paradox, has divided physicists for decades. Then there's the firewall paradox. Imagine crossing the event horizon. According to relativity, you'd feel nothing at first, a principle called no drama. But quantum mechanics suggests something far more violent, a wall of high-energy particles incinerating anything that passes through. Both can't be true, so which one is wrong? The answer could rewrite our understanding of space-time itself. Recent breakthroughs are bringing these theories out of the realm of pure math and into the realm of testable science. The Event Horizon Telescope's first image of a black hole's shadow in 2019 was a monumental leap, confirming predictions about how gravity bends light around these monsters. Now, scientists are pushing further, studying the chaotic orbits of stars near supermassive black holes, and even listening for the faint echoes of black hole mergers through gravitational waves. Each discovery peels back another layer of the mystery, but the wildest possibilities lie in the unknown. Some theories suggest black holes could be gateways to other universes, their singularities birthing entirely new cosmoses. Others propose that what we call a singularity might be replaced by something stranger, a dense, exotic state of matter where space-time becomes quantum foam. One thing's certain, black holes aren't just destructive anomalies, they're cosmic puzzles pressing us to ask deeper questions about reality itself. And as we inch closer to unraveling their secrets, we might just find the missing link between gravity and the quantum world, a key to unlocking the universe's greatest mysteries. What if the universe we experience, with its vast galaxies, swirling planets, and the very fabric of space-time, is nothing more than an elaborate projection, like a cosmic movie playing on a screen we can't see? This isn't the plot of a sci-fi film. It's the holographic principle, one of the most radical theories in modern physics. The idea suggests that all the information encoding our three-dimensional reality might actually live on a two-dimensional surface at the edge of the cosmos, like a hologram where depth is an illusion. It's a concept that turns our understanding of existence inside out, and it all started with a surprising discovery about black holes. When scientists first realized that black holes have entropy, a measure of disorder, they stumbled onto something profound. Entropy implies information, and the amount of information a black hole can hold isn't proportional to its volume, as you'd expect, but to its surface area. This bizarre observation led physicists like Gerard T. Hooft and Leonard Susskind to propose that maybe the universe works the same way. Think of it like this: everything happening in a room, every conversation, every movement, could theoretically be encoded on the walls surrounding it with no loss of detail. If true, our perceptions of depth, distance, and even time might just be a convenient trick of the cosmic code. But how could we possibly test such an outlandish idea? Enter quantum entanglement, the strange phenomenon where particles remain connected across vast distances, instantly influencing each other's states. Some researchers believe the way entangled particles interact could reveal hints of a hidden, lower-dimensional framework beneath our reality. Experiments like Fermilab's holometer have already started searching for microscopic jitters in space-time, tiny fluctuations that might betray the pixelated nature of the universe. Meanwhile, gravitational wave detectors like LIGO could uncover subtle patterns in ripples of space-time that align with holographic predictions. The implications are staggering. If the holographic principle holds, it would mean that free will, consciousness, and even the passage of time might be emergent properties of a deeper, information-based reality. It's as if we've been living inside a simulation, except the computer is the universe itself, running on rules we're only beginning to decipher. And here's the real kicker: this isn't just about physics. Philosophers and neuroscientists are now grappling with whether our very experience of reality could be a kind of controlled hallucination, shaped by the limits of how information is processed, by the cosmos and by our brains. Yet for all its elegance, the holographic principle leaves us with more questions than answers. If reality is a projection, what's projecting it? Could other universes be encoded on their own distant surfaces, like bubbles in an infinite cosmic foam? And if space-time isn't fundamental, what is? These aren't just abstract musings, they're clues that could lead us to the next great unification of physics, where gravity, quantum mechanics, and the nature of existence itself finally click into place. Until then, the universe remains the ultimate puzzle, teasing us with the possibility that everything we know might just be the surface of something far stranger. What if the key to unlocking the universe's deepest secrets isn't a particle, or a wave, or even a point, but a tiny, vibrating loop? That's the bold promise of string theory, a framework so ambitious it aims to stitch together all the forces of nature into a single, elegant equation. Picture the fundamental building blocks of reality not as dots, but as unimaginably small strings, each vibrating at different frequencies like the strings of a cosmic guitar. The pitch of their vibration determines whether they manifest as an electron, a quark, or even a graviton, the hypothetical particle carrying gravity itself. But here's the twist: these strings don't dance in the 3 dimensions we know. They require at least 10 dimensions to exist, with the extra ones curled up so tightly we'd never notice them in everyday life. The allure of string theory lies in its potential to be the theory of everything, bridging the chasm between quantum mechanics and general relativity. It elegantly sidesteps the mathematical nightmares that plague other approaches, offering a way to describe gravity at the quantum scale without equations exploding into infinities. But beauty in math doesn't always translate to proof in reality. To date, no experiment has directly detected these strings or their higher dimensions. Some critics argue the theory is more philosophy than physics, a dazzling castle in the air with no foundation in observable evidence, yet the search for validation is far from over. If extra dimensions exist, the Large Hadron Collider might someday produce microscopic black holes or missing energy signatures, hinting at particles escaping into hidden realms. Cosmic observations could reveal subtle imprints of string vibrations in the afterglow of the Big Bang. And then there's the mind-bending concept of brain worlds, where our entire universe is a three-dimensional brain floating in a higher dimensional space, like a sheet of paper drifting in a vast cosmic ocean. Collisions between brains could explain events as cataclysmic as the Big Bang itself. String theory also opens the door to a staggering multiverse scenario. The math suggests there could be 10 to the power of 500 possible configurations for these extra dimensions, each giving rise to a universe with its own unique laws. In this landscape, our universe's finely tuned constants might just be a random roll of the dice, with countless other realities existing where physics plays by entirely different rules. But not everyone is convinced. Rival frameworks like loop quantum gravity reject the need for extra dimensions altogether, proposing instead that space itself is woven from interconnected loops. The debate between these camps isn't just academic, it's a clash of worldviews. Should we trust a theory that's mathematically harmonious but lacks experimental proof, or hold out for something more grounded? For now, string theory remains the most compelling candidate for unification, even as it forces us to confront profound questions about the nature of evidence and the limits of human imagination. After all, if the universe is written in the language of vibrating strings, we're still learning how to read the notes. While string theory stretches our imagination with hidden dimensions, loop quantum gravity takes a radically different approach. It suggests space-time isn't smooth or continuous at all, but stitched together from tiny, indivisible loops. Imagine the fabric of reality not as a blank sheet but as an intricate mesh, like a cosmic chainmail where each link represents the smallest possible unit of space. These loops don't exist within space-time, they are space-time, woven into a dynamic network that evolves and interacts. This bold idea doesn't just tweak Einstein's relativity, it rewrites the rules at the most fundamental level. One of loop quantum gravity's most striking predictions is that singularities, those infinitely dense points at the heart of black holes and the Big Bang, simply can't exist. Instead of collapsing into a mathematical absurdity, the theory suggests gravity becomes repulsive at extreme densities, like a cosmic trampoline pushing back. Picture the Big Bang not as a singularity but as a big bounce, where a previous universe contracted to a tiny, hot state before rebounding into our expanding cosmos. Suddenly, the question, what happened before the Big Bang, isn't meaningless. It might have been the death throes of an earlier universe, cycling through an eternal dance of collapse and rebirth. The math behind this theory is as elegant as it is complex. Space is quantized, meaning there's a smallest possible volume, a graininess to reality you'd only notice if you could zoom in to a scale 1 trillion times smaller than an atom. Time, too, is pixelated, advancing in discrete ticks rather than a smooth flow. This granular structure solves a major headache in physics, the infinities that plague theories trying to merge quantum mechanics and gravity. In loop quantum gravity, space-time's quantum nature prevents those infinities from ever arising, offering a cleaner, more self-consistent framework. Yet the theory isn't without its challenges. Unlike string theory, which naturally includes all fundamental forces, loop quantum gravity focuses narrowly on quantizing gravity itself. Some critics argue it's like building a beautiful engine without a car to put it in brilliant in isolation, but incomplete as a full theory of everything. And while it avoids the need for extra dimensions, it introduces its own abstractions like spin networks, graphs where nodes represent quantized volumes of space and edges symbolize how they connect. Visualizing these structures requires a leap of imagination as daring as anything in string theory. What makes loop quantum gravity so compelling, though, is its grounding in observable physics. It makes testable predictions, like subtle modifications to the speed of light at extremely high energies or faint imprints, left on the cosmic microwave background from the universe's quantum infancy. Future experiments, like ultra-precise measurements of gamma-ray bursts or gravitational waves, could one day reveal whether space-time really is woven from loops. Until then, the theory stands as a powerful reminder sometimes the most revolutionary ideas come not from adding layers to reality, but from reimagining the very threads that hold it together. What if every choice you've ever made, every path taken or left unexplored exists somewhere out there in a parallel reality? The multiverse hypothesis isn't just a wild thought experiment. It's a serious scientific idea with roots in some of physics' most robust theories. Take cosmic inflation, for instance. According to this model, the universe expanded exponentially in the first fraction of a second after the Big Bang. But what if inflation didn't stop everywhere at once? Some regions could still be stretching, giving birth to new universes like bubbles in a boiling pot, each with its own unique laws of physics, constants, and even dimensions. String theory adds another layer to this cosmic tapestry. With its landscape of possible vacuum states, each representing a different universe, the math suggests there could be 10 to the power of 500 distinct realities. That's a number so vast it dwarfs the atoms in our observable universe. In some of these worlds, gravity might be stronger, electromagnetism weaker, or the very concept of matter unrecognizable. And then there's quantum mechanics, where the many worlds interpretation proposes that every quantum decision spawns a branching tree of realities. Did the cat in Schrödinger's thought experiment live or die? In this view, both outcomes happen just in separate, equally real timelines. But how could we ever prove something as extravagant as the multiverse? Traditional science demands testable predictions, and parallel universes, by definition, lie beyond our observational reach. Or do they? Some researchers speculate that if another universe bumped into ours long ago, it might have left a faint imprint in the cosmic microwave background, like a cosmic fingerprint. Others suggest that anomalies in the distribution of matter or energy across the sky could hint at a neighboring universe's gravitational tug. These ideas are speculative, but they offer a glimmer of hope that the multiverse might one day move from philosophy to physics. The philosophical implications are just as dizzying. If infinite universes exist, does that mean there's a version of you who became an astronaut, or one where dinosaurs never went extinct? Does it render our choices meaningless, or does it underscore the rarity of a universe like ours fine-tuned for life? And if other realities are forever out of reach, does the multiverse remain science, or does it cross into metaphysics? Critics argue that without empirical evidence, the multiverse is little more than a modern myth, a comforting story we tell ourselves to explain the improbable luck of our universe's conditions. Yet supporters counter that it's the natural extension of our best theories. a framework that solves puzzles like the fine-tuning problem without invoking supernatural explanations. Whether the multiverse is real or not, it forces us to confront the limits of human knowledge. Are we alone in existence, or just one thread in an infinite cosmic tapestry? The answer, if there is one, might lie not in the stars, but in the spaces between the equations we've yet to write. We think of the Big Bang as the ultimate beginning, the moment when space, time, and matter burst into existence. But what if that fiery instant wasn't a true starting point at all? The deeper we dig into cosmology, the more clues suggest that our universe's birth might be just one chapter in a much grander story. Take the cyclic model, for example. Picture two parallel sheets of space-time drifting toward each other in a higher dimensional realm. When they collide, the energy ignites a new Big Bang, creating a fresh universe while erasing traces of the old. Instead of a single explosive origin, this theory proposes an endless dance of creation and destruction, with universes rising and falling like waves in an eternal cosmic ocean. Then there's bouncing cosmology, a cousin to loop quantum gravity's vision of a big bounce. Here, the Big Bang wasn't a beginning but a rebound, a moment when a previous universe, crushed to an unimaginable density, snapped back outward in a new expansion. The equations suggest that such a bounce would smooth out irregularities, explaining why our infant universe was so remarkably uniform. It's as if the cosmos has a built-in reset button, recycling itself over and over across eons we can scarcely fathom. But perhaps the most mind-bending idea is that the Big Bang emerged from pure quantum randomness. In the seething foam of a primordial void, tiny fluctuations in energy could have sparked a runaway expansion, birthing our universe from nothing more than a statistical fluke. If true, this would mean time itself might not have existed before the Big Bang, because without a universe, there's no framework for before to even make sense. The search for answers isn't just philosophical. Telescopes like the James Webb Space Telescope are peering back to the universe's first light, hunting for faint patterns in the cosmic microwave background that could reveal whether our cosmos is alone or one of many. Some theories predict telltale swirls in this ancient radiation, evidence of a pre-Big Bang phase. Others look for gravitational waves from the inflation era, ripples that might carry whispers of what, if anything, came before. What's at stake isn't just the story of our universe, but the nature of reality itself. If the Big Bang was a one-time event, it leaves us with haunting questions about why it happened at all. But if it's part of an infinite cycle or a quantum accident in a multiverse, it reshapes our place in the cosmos. We might be living in just one bubble among countless others, each with its own laws, its own history, its own version of time. The deeper we probe, the more the universe defies our longing for a simple origin story, and that's where the real mystery begins. Just moments after the Big Bang, something extraordinary happened. The universe didn't just expand, it exploded in size, stretching faster than the speed of light itself. In less time than it takes light to cross a single proton, the cosmos ballooned by a factor of 10 to the power of 26, smoothing out wrinkles in space-time like a cosmic iron. This runaway expansion, known as cosmic inflation, wasn't just a growth spurt, it was the universe's ultimate makeover, solving mysteries that had baffled scientists for decades. Take the horizon problem. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see a uniform temperature across the sky, as if regions now billions of light years apart were once close enough to share heat. But without inflation, they'd never have had time to reach equilibrium. It's like walking into a bakery where every cookie, no matter where it's placed, is perfectly identical. Something had to mix the batter thoroughly before baking. Inflation does exactly that, stretching a tiny, homogeneous patch of space into the vast universe we see today. Then there's the flatness problem. The universe's geometry is eerily balanced between open and closed, like a pencil standing perfectly on its tip. Without inflation's smoothing effect, even a slight curvature in the early universe would have magnified into dramatic warping over billions of years. Inflation flattens space-time the way blowing up a balloon smooths out its creases, making the cosmos appear flat on observable scales, no matter its initial shape. But what fueled this breakneck expansion? The leading suspect is a hypothetical scalar field called the inflaton, a kind of cosmic energy syrup that temporarily overpowered gravity. As this field decayed, it released energy that reheated the universe, seeding it with the matter and radiation we know today. Yet some theorists argue the inflaton might not be the whole story. Could inflation have been triggered by collisions between higher dimensional brains, as string theory suggests? Or was it a phased transition in space-time itself, like water freezing into ice? The hunt for proof is on. Inflation should have generated gravitational waves, ripples in space-time that could still linger in the cosmic microwave background as a faint swirling pattern called B-mode polarization. Experiments like BICEP and the upcoming Lightbird satellite are scouring the sky for these primordial fingerprints, but critics aren't convinced. Some propose alternatives like variable speed of light theories, where light traveled faster in the early universe, eliminating the need for inflation altogether. Others suggest the universe didn't inflate once but cyclically, with periods of expansion and contraction. The stakes couldn't be higher. If inflation happened, it didn't just shape our universe, it might have spawned countless others, each with its own physics in an endless multiverse. Yet if alternatives prevail, we'd need to rewrite cosmology's opening chapter. One thing's certain, the universe's first moments were far stranger than we ever imagined, and the clues to unlocking them are still out there, written in the fabric of space itself. One of quantum mechanics' most bewildering implications is that particles seem to exist in multiple states at once, until someone looks. An electron isn't just here or there, it's everywhere it could possibly be, a blur of probabilities known as a wave function. But the instant we measure it, that fuzzy potential snaps into a single, definite reality. This is the measurement problem, and it's sparked a century of debate. Does consciousness itself play a role in shaping the universe? The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, treats measurement as the ultimate arbiter of reality. In this view, the wave function isn't just a mathematical tool, it's the true state of a system until observation forces it to collapse. But here's the catch, the theory doesn't define what counts as an observer. Is it a human scientist, a camera, a single atom bumping into another? The vagueness has led some to speculate that consciousness might be the missing ingredient, a notion popularized by physicist John von Neumann. If true, it would mean the universe exists in a hazy, unresolved state until a mind perceives it, an idea that edges perilously close to philosophy. Enter the many worlds interpretation, which sidesteps the issue entirely. Instead of collapsing, the wave function branches endlessly, spawning parallel realities where every possible outcome plays out. In this scenario, there's no special role for consciousness, just an infinite tree of diverging timelines. Yet this raises its own questions. Why do we experience only one branch? And where do all those other versions of reality actually exist? Then there's objective collapse theories, which propose that wave functions collapse spontaneously due to some as yet unknown mechanism in nature, no observer required. Experiments like those searching for gravitational effects on quantum systems aim to test this idea. But the most radical proposition, that space-time itself emerges from quantum interactions, meaning the distinction between observer and observed might be an illusion. At the heart of this debate is a profound philosophical rift. If consciousness influences reality, does that imply the universe is somehow participatory, a cosmic dance between mind and matter? Or is this just a quirk of our incomplete theories, a placeholder until deeper physics renders the question obsolete? The answer could redefine not just how we understand quantum mechanics, but what it means to exist in the cosmos at all. Time feels like the most familiar part of our existence, an ever-flowing river carrying us from past to future. But here's the paradox: the laws of physics don't actually care which way time moves. At the microscopic level, particles behave the same whether time runs forward or backward. So why does our universe stubbornly insist on moving in one direction? The answer lies in a deceptively simple concept: entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time, giving us an arrow pointing unambiguously toward the future. A shattered glass doesn't reassemble itself. Smoke never retreats neatly into a cigarette. These everyday experiences are all echoes of entropy's relentless rise, but this raises a deeper puzzle. If entropy only grows, why was it so astonishingly low in the early universe? Picture the Big Bang, a state of near-perfect order, a hot, dense soup where particles were almost uniformly distributed. That's like finding a pristine sandcastle in the middle of a windstorm. How did it get there? This is the essence of the past hypothesis, the idea that our universe began in an exceptionally low entropy state for reasons we don't yet understand. Some theorists suggest quantum fluctuations in a pre-Big Bang era might have set the stage, while others propose that gravity, warping space-time itself, could have acted as an entropy-reducing force in those first moments. Then there's the radical notion that time might not be fundamental at all. In quantum gravity theories like loop quantum gravity, time disappears entirely from the equations at the most basic level, emerging only as a macroscopic effect, like how temperature arises from the motion of atoms. If true, our experience of time's flow could be an illusion, a cosmic sleight of hand. Even black holes hint at this possibility. Near the event horizon, time slows to a crawl relative to distant observers, and at the singularity, it might cease to have meaning altogether. Experiments are now probing time's nature in ways Einstein could only dream of. Quantum systems can exhibit retrocausality, where measurements made in the present seem to influence events in the past. And in labs worldwide, physicists are creating exotic states of matter where entropy temporarily decreases, teasing out the conditions that might have existed at the dawn of time. The implications stretch far beyond physics. If time's arrow isn't absolute, what does that mean for free will or the inevitability of cause and effect? Could a universe with no preferred direction of time even sustain life as we know it? Every clue we uncover pulls us deeper into the mystery, revealing that time isn't just a backdrop to existence. It might be the most profound puzzle the universe has left us to solve. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace. Nearly massless and indifferent to matter, they're cosmic phantoms, slipping through planets and stars like they aren't even there. Yet these elusive particles, once thought to be mere afterthoughts in physics, are now at the heart of some of science's biggest mysteries. Take neutrino oscillations, for example. These particles come in three flavors: electron, muon, and tau, but they don't stay put. A neutrino born in a distant supernova might start its journey as one type and arrive at Earth as another, shape shifting mid-flight like a chameleon crossing dimensions. This bizarre behavior, confirmed by experiments like Super Kamiokande in Japan, implies something revolutionary. Neutrinos have mass, however tiny, and that shakes the foundations of the Standard Model, the rulebook for particle physics, which long assumed these particles were weightless. The hunt to decode neutrinos has spawned some of the most ambitious experiments ever conceived. Deep beneath the Antarctic ice, the ice cube detector watches for faint blue flashes, signals of neutrinos colliding with atoms, their rare interactions captured in a cubic kilometer of ultra-clear ice. These particles, traveling from cataclysmic events like colliding black holes or dying stars, are cosmic messengers carrying secrets from the farthest reaches of space. Meanwhile, the Deep Underground Neutrino Experiment, or DUNE, will fire beams of neutrinos through 800 miles of Earth from Illinois to South Dakota, probing their oscillations with unprecedented precision. The goal, to uncover whether neutrinos and their antimatter counterparts, antineutrinos, behave differently, a clue to one of the universe's greatest enigmas, why we exist at all. Here's why that matters. In the first moments after the Big Bang, matter and antimatter should have annihilated each other, leaving behind a lifeless sea of energy. Yet somehow, matter won out and neutrinos might hold the key. If they violate something called charge parity symmetry, tipping the scales ever so slightly in favor of matter, it could explain how a universe of galaxies, planets, and people emerged from nothing. But neutrinos aren't just relics of the past, they are also windows into the present. When a star explodes as a supernova, 99% of its energy bursts outward as neutrinos, arriving at Earth hours before the light does. Detecting these particles could give us an early warning system for stellar deaths, letting us train telescopes on the sky before the fireworks even begin. And then there's the dream of spotting relic neutrinos from the Big Bang itself, a faint background hum from the birth of the cosmos, waiting to be heard. What makes neutrinos so thrilling isn't just what we've learned, it's how much remains hidden. They defy expectations at every turn, challenging our models and pushing technology to its limits. Whether they're revealing the inner workings of collapsing stars or rewriting the rules of particle physics, one thing's clear: the universe's quietest particles might just have the loudest things to say. The universe is unimaginably vast, billions of galaxies, each with billions of stars, most likely orbited by even more planets. With numbers like these, the odds seem overwhelming that life, even intelligent life, should be common. And yet, when we look out into the cosmic ocean, we're met with silence. No signals, no artifacts, no signs of other civilizations. This eerie contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" One possible answer lies in something called the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar scales. The terrifying possibility is that the filter might still be ahead of us. Maybe civilizations routinely reach a certain technological level, like ours, only to trigger their own destruction through war, environmental collapse, or unchecked artificial intelligence. If true, the silence of the cosmos could be a warning written in the stars. But there's another, less grim option. Perhaps the filter is behind us. Maybe the leap from simple chemistry to self-replicating life is so astronomically rare that Earth is a cosmic fluke, a lonely island of consciousness in an otherwise lifeless void. Then there's the zoo hypothesis, the idea that advanced civilizations exist but deliberately avoid contact, observing us like animals in a galactic nature preserve. It's a chilling thought. What if we're not just alone, but intentionally isolated? Some theories go even further, suggesting that sufficiently advanced beings might have transcended physical forms altogether, uploading their minds into virtual realities or even manipulating the fabric of space-time to exist outside our perceptual limits. If aliens have harnessed higher dimensions or mastered quantum communication, we might literally lack the senses to detect them. Recent discoveries add another layer to the mystery. Telescopes like Kepler and James Webb have confirmed thousands of exoplanets, some in the so-called Goldilocks zone where liquid water, and thus life as we know it, could exist. Yet despite scanning for biosignatures like oxygen or methane in alien atmospheres, we've found nothing definitive. The paradox deepens. If the ingredients for life are everywhere, why does it seem so absent? Perhaps the answer isn't about space but time. Civilizations might rise and fall in cosmic moments too brief to overlap. Imagine two fireflies blinking in the night. If their flashes don't sync, they'll never know the other was there. Or maybe we're asking the wrong questions entirely. Our search assumes aliens would communicate via radio waves or leave visible megastructures. But what if their technology operates on principles we haven't even imagined yet? The Fermi paradox isn't just a puzzle, it's a mirror. Every possible solution forces us to confront our place in the universe. Are we the first, the last, or simply the only ones? Until we know for sure, the silence of the cosmos remains both a mystery and an invitation to keep looking, listening, and wondering. Because one day, the answer might not just change science, it could change everything. Einstein's equations revealed something straight out of a sci-fi novel. Hidden within the math of general relativity are tunnels that could theoretically connect distant points in space-time, or even different universes. These cosmic shortcuts, known as wormholes, aren't just fantasy. They're legitimate solutions to the equations that govern gravity. Picture space-time as a sheet of paper, folded so 2 points touch. A wormhole would be like poking a pencil through that fold, creating a bridge that bypasses the distance between them. The catch, keeping that tunnel stable, requires something bizarre: exotic matter with negative energy, a substance that defies gravity by pushing space-time outward instead of pulling it inward. So far, exotic matter exists only in theory, often linked to quantum phenomena like the Casimir effect, where tiny particles pop in and out of existence in a vacuum, generating fleeting negative energy. But to prop open a wormhole large enough for even a single atom, you'd need vast amounts of this elusive material far beyond what current physics can explain. That hasn't stopped theorists from dreaming. Some propose that advanced civilizations mastering quantum engineering might one day harvest enough exotic matter to stabilize these tunnels, turning interstellar travel into a matter of stepping through a cosmic door. Even wilder is the idea that wormholes might already exist on microscopic scales, woven into the quantum foam of space-time. These would be far too small for humans to traverse, but their existence could rewrite our understanding of reality. Recent experiments have added fuel to the fire. In 2022, physicists used a quantum computer to simulate a holographic wormhole, showing how information could teleport between entangled particles in a way that eerily mirrors predictions about wormhole dynamics. It's not proof that wormholes exist, but it's a tantalizing hint that the universe's strangest phenomena might share hidden connections. Then there's the time travel dilemma. If wormholes link not just space but different moments in time, could they become portals to the past or future? The math suggests yes, but with mind-bending constraints. A wormhole time machine would require one end to be accelerated to near light speed or placed near an intense gravitational field, like a black hole, warping time so drastically that the two ends would exist in different eras. Even then, paradoxes loom. Step through and meet your past self, and you might trigger a chain of logical impossibilities that physics simply can't resolve. Some theorists argue quantum mechanics could enforce a cosmic censorship, preventing such paradoxes by collapsing the wormhole the instant a contradiction arises. The line between science and speculation has never been thinner. While wormholes remain firmly in the realm of theory, they force us to ask profound questions about the nature of space, time, and the limits of human ingenuity. Could they someday revolutionize travel, or are they destined to remain cosmic mirages? The answer might lie in the next great unification of physics, where relativity, quantum mechanics, and the universe's deepest secrets finally collide. Imagine two coins flipped on opposite sides of the galaxy. No matter how far apart they are, they always land showing the same face. That's the essence of quantum entanglement, one of the most baffling phenomena in physics. When particles become entangled, their properties are mysteriously linked, so that measuring one instantly determines the state of the other, even if they're separated by light years. Einstein famously called this spooky action at a distance, dismissing it as evidence that quantum mechanics must be incomplete. But decades of meticulous experiments have proven him wrong. The universe really does operate this way, and the implications are staggering. Take the Nobel Prize-winning work of Alain Aspect, John Clauser, and Anton Zeilinger. Their experiments closed every conceivable loophole in tests of Bell's theorem, a mathematical framework distinguishing quantum weirdness from classical physics. By entangling particles and measuring their properties at distances too great for any hidden signal to travel between them, even at the speed of light, they confirmed that entanglement violates local realism. In other words, reality isn't just what's happening here and now. It's somehow interconnected across vast stretches of space in ways that defy intuition. But here's the real twist. Entanglement doesn't just challenge our ideas about particles. It might redefine our understanding of space itself. Some theories, like equals epper, propose that entangled particles are connected by microscopic wormholes, threading through the fabric of space-time like invisible stitches. If true, entanglement wouldn't be a bizarre exception to the rules of reality. It would be the very foundation of how space-time is woven together. Picture the universe as a vast network of entangled relationships, where the distances between objects are illusions, and the true structure of reality is a web of quantum connections. This perspective flips the script on relativity's cosmic speed limit. While nothing can travel faster than light through space, entanglement suggests that information might bypass space altogether, operating on a deeper layer of reality. It's as if the universe has a hidden backstage where the usual rules don't apply. Experiments in quantum gravity are now testing these ideas, probing whether space-time emerges from a sea of entangled quantum bits, like a 3D hologram projected from a 2D surface. The implications ripple outward. If entanglement underpins space-time, it could explain why black holes preserve information instead of destroying it, because their interiors might remain entangled with the radiation they emit. It could even hint at a resolution to the conflict between quantum mechanics and gravity, offering a path toward the long-sought theory of everything. But the most profound realization is this: the universe isn't just a collection of isolated objects moving through empty space. It's a dynamic, interconnected whole, where the act of observing one particle can rewrite the state of another halfway across the cosmos. And that's not just spooky, it's revolutionary. What if everything around us, the stars, the planets, even the thoughts in your mind, weren't real, but lines of code in an unfathomably advanced simulation? The simulation hypothesis, once relegated to science fiction, has gained surprising traction among scientists and philosophers. At its core is a simple but unsettling idea. If civilizations inevitably create hyper-realistic simulations of their ancestors, the odds suggest we're far more likely to be inside one than in the original universe. Think of it like this: if there's only one base reality but countless simulated worlds, the math says you're probably not in the one true version. The roots of this theory stretch back to quantum mechanics, where particles exist in probabilistic states until observed, almost as if rendering only what's needed to conserve computational resources. Then there's the pixelation of space-time suggested by loop quantum gravity, where the universe appears smooth at large scales but grainy up close, like the pixels on a screen. Even cosmic speed limits, like the speed of light, could be seen as processing constraints, preventing the simulation from overloading. Some theorists point to potential glitches in physical laws, like the slight variations in fundamental constants or the way particles sometimes behave differently when measured, as possible artifacts of an imperfect simulation. But the most compelling argument comes from the mathematical nature of reality itself. The universe operates with astonishing precision, following equations that can be written on a napkin, yet describe everything from galaxy formation to chemical bonds. This has led some, like physicist Max Tegmark, to propose that reality isn't just described by math, it is math. In this view, our universe could be a mathematical structure running on some cosmic computer, with the laws of physics as its operating system. Critics dismiss the hypothesis as untestable metaphysics, a modern-day version of asking whether we're living in a dream. Yet a few bold experiments have been proposed. One involves searching for computational shortcuts in high-energy physics, signs that the universe cheats by not calculating details until observed. Another looks for anomalies in cosmic rays, which might reveal a pixelated structure to space-time if the simulation's resolution isn't fine enough. The implications are dizzying. If we're in a simulation, does free will exist, or are our choices predetermined by code? Could the programmer intervene, or are we left to our own emergent rules? And if simulations can spawn nested simulations, how many layers deep does reality go? The hypothesis doesn't just challenge our place in the cosmos, it redefines what real even means. Whether it's true or not, it forces us to confront the humbling possibility that our understanding of existence might be as limited as a character in a video game trying to grasp the player holding the controller. Einstein's theory of general relativity has been the gold standard for understanding gravity for over a century. But what if it's not the whole story? The discovery of dark matter and dark energy has forced scientists to confront an uncomfortable truth. Either the universe is filled with invisible, unexplained substances, or our equations for gravity are missing something fundamental. This dilemma has given rise to a bold alternative: modified gravity theories, which propose tweaking Einstein's rules to explain cosmic mysteries without invoking dark matter or energy. The most famous of these is modified Newtonian dynamics, or MUND, a framework that suggests gravity behaves differently at extremely low accelerations, like those found in the outskirts of galaxies. At first glance, MUND seems to solve one of astronomy's biggest headaches: the strange rotation of galaxies. Stars orbiting a galaxy's edge move far faster than Newton's or Einstein's laws predict unless there's a halo of invisible dark matter tugging on them. Buttman claims you don't need dark matter at all. Adjust gravity's equations slightly, and the observed rotations match perfectly. It's an elegant solution, and for certain galaxies, it works astonishingly well. Yet the theory stumbles when faced with larger scales. Galaxy clusters, for instance, still seem to require some form of unseen mass to account for their gravitational pull, even under MUND adjustments. And then there's the cosmic microwave background, the afterglow of the Big Bang. Its intricate patterns align almost perfectly with dark matter models, but clash with MUND predictions unless, ironically, you add a sprinkle of unseen particles back into the mix. The debate gets even thornier when dark energy enters the picture. Could modified gravity explain the universe's accelerating expansion without invoking this mysterious force? Some theories, like tensor vector scalar gravity (TVS), attempt to extend ideas to cosmic scales, proposing that space-time itself behaves differently over vast distances. But these models struggle to match the precision of general relativity's predictions for phenomena like gravitational lensing or the motion of binary pulsars. Even more damning, when physicists tested predictions against new data from the Gaia satellite, a mission mapping billions of stars, the results were ambiguous at best, failing to deliver the knockout blow its proponents hoped for. So why does modified gravity still captivate scientists? Because it forces us to question assumptions. Maybe dark matter and dark energy are real, but their elusiveness suggests we're missing a piece of the puzzle. Or perhaps gravity isn't a fixed force but something more fluid, changing depending on scale or environment. The answer might lie in the uncharted territory where quantum mechanics and relativity collide, a realm where space-time could emerge from deeper quantum interactions, rewriting the rules entirely. For now, the jury's out. Modified gravity remains a provocative underdog, challenging the mainstream while grappling with its own limitations. But that's the beauty of science. Even the most radical ideas push us closer to the truth, whether by proving themselves or revealing where the old models break down. The universe isn't obligated to fit neatly into our equations, and that's what makes the search so thrilling. Black holes aren't just cosmic vacuum cleaners. They're the universe's ultimate shredders, swallowing stars, planets, and light itself without a trace. But here's where things get weird. Quantum mechanics insists that information can never truly be destroyed, while black holes seem to erase it completely. This contradiction lies at the heart of the black hole information paradox, a puzzle so profound it threatens to upend our understanding of reality. When Stephen Hawking first proposed radiation escaping from black holes, it seemed like a breakthrough, until physicists realized those escaping particles carried no information about what fell in. If black holes evaporate completely, where does the swallowed information go? Does it vanish into nothingness, violating quantum law, or is there some cosmic sleight of hand at work? One radical solution suggests the answer is as violent as it gets: firewalls. Picture the event horizon not as an invisible boundary, but as a searing wall of high-energy particles, incinerating anything that crosses it. In this scenario, information isn't lost, it's scrambled into thermal radiation so thoroughly that reconstructing it would be like trying to reassemble a burned book from its ashes. The firewall preserves quantum rules, but at a terrifying cost. Einstein's no drama principle, which states that crossing the horizon should feel uneventful, gets torched along with the unlucky astronaut. Then there's the soft hair hypothesis, a more graceful solution inspired by the mathematics of black hole surfaces. Just as a fuzzy peach has tiny hairs, black holes might carry subtle quantum imprints, low-energy particles clinging to their horizons like cosmic graffiti. These faint signatures could encode information about everything that ever fell in, preserving it in distortions so delicate they're practically invisible. It's as if the black hole keeps a secret diary written in vanishing ink, one that only reveals itself through quantum decryption. But the most mind-bending answer comes from holography. If the universe stores information on boundaries rather than in volumes, like a 3D movie projected from a 2D screen, then a black hole's interior might be an illusion. The real data could live encoded on its event horizon, with Hawking radiation acting as a cosmic USB drive, slowly transferring that information back out as the hole evaporates. Recent breakthroughs in quantum gravity even suggest that black holes might create entangled copies of infalling information, preserving it in a form that scrambled but not destroyed. The stakes couldn't be higher. If information can vanish without a trace, the foundation of quantum mechanics crumbles, and with it our ability to predict anything about the universe's behavior. But if solutions like holography or soft hair hold, they could reveal something even more astonishing. That space-time itself is a kind of quantum error-correcting code, built to preserve information at all costs. Every photon, every atom, every thought might be etched into the fabric of reality in ways we're only beginning to decipher. And that means black holes aren't just cosmic dead ends, they're the ultimate encryption devices, challenging us to crack the universe's deepest secrets. Cosmic strings sound like something from mythology, threads woven through the cosmos so dense a single inch would outweigh Mount Everest. Yet these hypothetical relics, predicted by grand unified theories, could be real defects in the fabric of space-time itself, frozen remnants of the universe's fiery birth. Picture the early cosmos cooling from an unimaginably hot plasma, like metal hardening after being forged. Just as cracks form when materials solidify unevenly, cosmic strings might have emerged as space-time itself underwent phase transitions in those first chaotic moments after the Big Bang. These wouldn't be ordinary strings, but unimaginably thin, infinitely long filaments of pure energy, stretching across billions of light years like cosmic fault lines. What makes them so fascinating isn't just their origins, it's how they'd warp reality around them. A cosmic string's gravitational pull would be so intense it could slice through space-time like a knife through fabric, bending light from distant galaxies into double images or creating razor-straight scars in the cosmic microwave background. Unlike black holes, which swallow everything nearby, strings would leave no shadows, just subtle distortions in their wake, clues written in the bending of starlight. Even more intriguing, they might vibrate like plucked guitar strings, sending ripples through space-time itself. These gravitational waves would carry a unique signature, far different from the chirps produced by colliding black holes, a low, steady hum echoing across the ages. The hunt for cosmic strings is a detective story with high stakes. If they exist, they'd offer a direct glimpse into the universe's first trillionth of a second, a time when the fundamental forces, gravity, electromagnetism, and the nuclear forces, were still unified as one. Future observatories like the Laser Interferometer Space Antenna, or LISA, could catch their gravitational whispers, while next-generation telescopes might spot the telltale kinks or cusps where strings intersect, releasing bursts of energy. Even pulsar timing arrays, which monitor the precise rhythms of spinning neutron stars, could reveal strings by detecting the way their gravitational waves disrupt the arrival times of these cosmic metronomes. Yet the absence of cosmic strings would be just as revealing. If searches come up empty, it could mean our theories about the early universe need a radical rewrite. Perhaps the phase transitions were smoother than predicted, or the energy scales involved were different. Either way, the quest to find them forces us to confront profound questions. Are these cosmic scars the fingerprints of a grand unification, or just another beautiful idea the universe has refused to confirm? The answer could rewrite not just the story of how everything began, but what the fabric of reality is truly made of. The vacuum of space isn't really empty, not even close. According to quantum field theory, what we call nothing is actually a seething, bubbling froth of virtual particles popping in and out of existence, a phenomenon known as vacuum energy. These fleeting fluctuations generate an energy density so immense that, if the math held true, the universe should have torn itself apart moments after the Big Bang. Yet when we measure the actual energy of empty space, what we now call dark energy, It's absurdly tiny, a discrepancy of 1 followed by 120 zeros. This staggering mismatch between prediction and reality is known as the vacuum catastrophe, and it's been called the worst theoretical prediction in the history of physics. So where did the math go so wrong? One leading suspect is supersymmetry, an elegant framework that posits every known particle has a hidden, heavier twin. If these superpartners exist, their contributions to vacuum energy could cancel out the extreme values predicted by standard quantum theory, leaving behind the subtle dark energy we observe. The catch, after decades of searching, colliders like the Large Hadron Collider have found no trace of these particles, leaving supersymmetry in limbo, beautiful in theory, but increasingly elusive in practice. Another radical idea is that we're missing a fundamental symmetry in nature, one that forces vacuum energy to exactly zero for reasons we don't yet grasp. Some theories suggest gravity itself might play a role, acting as a cosmic dampener that suppresses quantum fluctuations on large scales. Others propose that the vacuum isn't uniform, but fragmented into domains with different energy values, and we just happen to live in a pocket where the number is unnaturally small. Then there's the anthropic principle, a controversial but tantalizing explanation. If the multiverse is real, with countless universes each hosting different vacuum energies, only those with values fine-tuned for life, like ours, would ever have observers to ponder the question. In this view, the vacuum catastrophe isn't a problem to solve but a selection effect. We're here because the numbers had to be just right. The implications stretch far beyond theory. If vacuum energy were even slightly stronger, galaxies would never have formed. If weaker, the cosmos would have collapsed long ago. This razor-thin balance hints at a deeper connection between quantum mechanics and gravity, one that might only reveal itself in the extreme environments of black holes or the first moments of the Big Bang. Solving the vacuum catastrophe could be the key to unlocking that union and rewriting our understanding of reality itself. Space-time might feel like the unchanging stage upon which the universe unfolds, but what if it's more like the surface of a lake, a shimmering illusion emerging from something far stranger? The latest theories in quantum gravity suggest that space and time aren't fundamental at all, but secondary phenomena, rising from a deeper layer of reality where entanglement and information are the true building blocks. Picture a three-dimensional hologram projected from a two-dimensional surface, except in this case, the surface is a network of quantum connections, and the hologram is our entire cosmos. This radical idea, known as emergent space-time, turns physics on its head, proposing that the geometry of the universe is woven from relationships between particles, not the other way around. Take black holes, those cosmic paradox machines. According to the holographic principle, all the information swallowed by a black hole isn't lost in its depths but encoded on its event horizon, the boundary where light can no longer escape. It's as if the interior of the black hole is an illusion, a shadow cast by quantum data painted on its surface. This isn't just poetic imagery. The math shows that the maximum entropy, the information capacity, of any region of space is proportional to its surface area, not its volume. In other words, the universe might fundamentally operate like a cosmic hard drive, with its true workings happening at the edges, not the bulk. But how could something as tangible as space-time emerge from abstract information? Experiments with quantum analogs are offering tantalizing clues. In labs around the world, physicists are simulating space-time using ultra-cold atoms or arrays of entangled qubits, creating artificial universes where emergent geometry can be studied like never before. Some of these experiments have already shown that certain quantum systems naturally give rise to properties that resemble gravity and dimensionality, as if space itself is a collective hallucination of underlying quantum bits. Imagine watching a movie and realizing the plot isn't driven by the characters, but by the pixels on the screen conspiring to create the illusion of motion. That's the scale of the revolution we're talking about. The implications ripple outward, challenging our deepest assumptions about causality and dimensionality. If space-time is emergent, then cause and effect might not be fixed pillars of reality, but fluid consequences of deeper quantum relationships. Time's arrow could be an artifact of increasing entanglement, a cosmic trend toward complexity rather than an intrinsic feature of the universe and dimensionality. It might not be a static backdrop, but a dynamic, fluctuating property. Some theories suggest extra dimensions could unfurl from the quantum foam under extreme conditions, like hidden folds in a cosmic origami. Even the Big Bang gets a rewrite in this framework. Instead of a singularity where space and time begin, the universe's birth might mark the moment when quantum information first crystallized into the geometry we recognize. Some models propose that the Big Bang was a phase transition, like water freezing into ice, where the chaotic quantum substrate cooled into the orderly structure of space-time. If true, the echoes of that transition could still be detectable in the quantum noise of the vacuum or the faintest gravitational waves, clues waiting in the static of the cosmos. The question isn't just academic. If space-time is emergent, then the next generation of telescopes and quantum sensors might soon uncover its seams, places where the illusion frays, revealing the informational underbelly of reality. Whether through anomalies in high-energy particle collisions, distortions in the cosmic microwave background, or unexpected patterns in quantum computers, the evidence could rewrite physics itself. And when it does, we won't just be understanding the universe, we'll be decoding the source code of existence. Time crystals sound like something ripped from the pages of a sci-fi novel. Structures that pulse and oscillate endlessly without any energy input, like a clock that winds itself. But these aren't fantasy, they're real, bizarre phases of matter that defy one of physics' most sacred principles, the arrow of time. Normally, everything in the universe marches toward equilibrium, like a cup of coffee cooling to room temperature or a pendulum eventually coming to rest. Time crystals flip this script, predicted in 2012 by Nobel laureate Frank Wilczek, and later created in labs using chains of ions or diamond defects. These structures don't settle into equilibrium. Instead, they lock into a rhythmic dance, repeating their motion indefinitely without losing energy, as if etching grooves into time itself. How is this possible? The secret lies in what's called time symmetry breaking. In everyday physics, the laws don't care if time runs forward or backward. Drop a ball, and the motion looks the same played in reverse. But time crystals spontaneously break this symmetry, choosing a preferred rhythm that repeats at fixed intervals, like a metronome ticking without being wound. They achieve this not by violating thermodynamics, but by exploiting quantum entanglement, where particles become so deeply linked that their collective behavior locks into a stable, repeating pattern. Imagine a row of dominoes that, instead of falling in a straight line, cycle endlessly in a loop, toppling and resetting without anyone touching them. That's the essence of a time crystal, a system that finds stability in perpetual motion. The implications are as profound as they are strange. For quantum computing, time crystals could be game changers. Traditional qubits, the building blocks of quantum computers, are notoriously fragile, collapsing at the slightest disturbance. But time crystals' inherent stability might offer a way to protect quantum information, acting as error-resistant memory cells in a future quantum processor. Experiments are already underway to harness their rhythmic properties for synchronizing quantum operations, like a conductor keeping an orchestra in perfect time. And then there's the tantalizing, if controversial, idea of perpetual motion. While time crystals don't violate the laws of thermodynamics, they don't produce energy, just recycle it. They blur the line between impossibility and ingenuity, challenging engineers to rethink what motion without input could mean for low-energy technologies. But perhaps the most mind-bending aspect isn't their potential applications, it's what they reveal about time itself. Physics has long treated time as a passive backdrop, a parameter that ticks uniformly across the universe. Time crystals suggest something far more dynamic, that time, like space, might have structures within it, patterns that emerge from the quantum fabric of reality. Could there be more exotic phases of matter that twist time in other ways? Some theorists speculate about time quasicrystals, with rhythms that never quite repeat, or even higher dimensional time crystals operating in realms beyond our perception. For now, these questions linger at the edge of known physics, but one thing's certain: time crystals aren't just curiosities. They're a doorway into a deeper understanding of how time, matter, and quantum mechanics intertwine, a reminder that even the most fundamental aspects of reality might still hold surprises waiting to be uncovered. The cosmic microwave background, the oldest light in the universe, should be a perfectly random snapshot of the Big Bang's afterglow, a celestial fingerprint with no preferred direction. Yet when scientists mapped its subtle temperature variations, they stumbled onto something unsettling: a bizarre alignment of hot and cold spots stretching across the sky like an invisible axis, nicknamed the Axis of Evil. This eerie pattern defies the foundational principle of cosmology, that the universe on large scales should look the same in every direction. If this isn't a statistical fluke, it could mean our cosmic rulebook is missing entire chapters. One of the most startling aspects of the axis is how it seems to align with the plane of our solar system, an absurd coincidence that feels less like physics and more like a cosmic prank. Standard inflationary models can't explain it. In fact, they predict such alignments should be vanishingly rare. So what's really going on? Some theorists suggest the anomaly might be a relic from before the Big Bang, a scar left by a previous universe that somehow imprinted its structure onto ours. Imagine a sheet of paper crumpled and then flattened. The creases remain, hinting at a history we can't see. If true, this would mean the Big Bang wasn't the absolute beginning but a transition, a rebirth from an earlier cosmos with its own geometry. Others propose more exotic explanations, like primordial magnetic fields woven through the fabric of space-time. These invisible force lines, stretching across billions of light years, could have twisted the infant universe's plasma like a cosmic whirlpool, leaving behind patterns that persist in the microwave background. There's even speculation that the axis could be evidence of a multiverse, a collision with another bubble universe nudging our own into asymmetry, like a fingerprint smudged by a passing hand. But not everyone's convinced. Skeptics argue the axis might just be a trick of perspective, a mirage created by the way we're embedded in the cosmic web. Or perhaps it's an artifact of incomplete data, a ghost in the machine that will vanish as telescopes like the James Webb probe deeper into the microwave background's secrets. The Planck satellite's meticulous maps have already ruled out some of the wilder theories, yet the anomaly stubbornly persists, gnawing at the edges of our models. The stakes are higher than they seem. If the axis is real, it doesn't just challenge inflation, it forces us to rethink whether the universe is truly isotropic, a bedrock assumption since Einstein. Resolving this puzzle could require entirely new physics, from modifications to gravity to radical revisions of quantum field theory. Or it might reveal something even stranger, that the cosmos has a hidden architecture, a skeleton we've only just begun to trace. Until then, the axis of evil remains one of cosmology's most tantalizing enigmas, a whisper from the void that the universe is far less random and far more mysterious than we ever imagined. If black holes are the universe's ultimate drains, sucking in everything that crosses their path, then white holes are their theoretical opposites, cosmic fountains gushing matter and energy outward with unstoppable force. The math of general relativity allows for these bizarre objects, but finding one is another story. Unlike their dark counterparts, white holes aren't just hard to spot, they defy the very arrow of time as we know it. Imagine a black hole running in reverse. Where a singularity would form, a white hole erupts, violently expelling everything it contains in a burst of light and particles. No spaceship could enter one. The sheer force of its output would repel anything trying to get close. The idea isn't just science fiction. White holes emerge naturally from the equations of general relativity, especially when paired with quantum mechanics. Some theorists suggest they could be the other end of a wormhole, linked to a black hole in a distant region of space-time. Others propose an even wilder possibility, that the Big Bang itself was a white hole event, a singularity not collapsing but exploding into our universe. Picture a black hole in some other cosmos collapsing to a point, then rebounding as a white hole, birthing an entirely new space-time continuum. It's a cosmic version of recycling, where the death of one universe becomes the birth of another. Yet the biggest hurdle isn't just their absence in observations, it's their inherent instability. White holes violate the second law of thermodynamics by seemingly creating order from chaos, spewing out pristine matter instead of entropy. Some models suggest they'd collapse instantly into black holes the moment real-world particles interacted with them, like a soap bubble popping at the slightest touch. Still, their theoretical allure is undeniable. If they exist, even fleetingly, they could redefine our understanding of singularities, showing that space-time's most extreme points aren't dead ends but gateways. The search continues in unexpected places. Some physicists scour gamma-ray bursts for unnatural signatures, sudden, symmetrical explosions that don't fit supernova or collision profiles. Others simulate white holes in quantum systems, recreating their behavior in lab-scale analogs. And then there's the tantalizing thought that dark matter anomalies or unexplained cosmic rays might be whispers of these elusive objects hidden in plain sight. Whether white holes are real or just mathematical phantoms, they force us to confront the limits of our theories. If they're out there, they're rewriting the rules of existence. If not, they're a reminder that the universe's strangest possibilities often lie just beyond the edge of what we can see. Quantum mechanics and general relativity are like two brilliant scientists speaking different languages. Both describe reality with astonishing accuracy, but their rulebooks clash violently when pushed to extremes. At the heart of this divide lies the elusive theory of quantum gravity, the missing framework that could stitch these cosmic puzzles together. Imagine trying to merge the chaotic, probabilistic world of subatomic particles with the smooth, geometric elegance of space-time. It's like blending a Jackson Pollock painting with a Renaissance masterpiece. The result, a scientific battleground where the leading theories each offer wildly different visions of reality's deepest layer. String theory, perhaps the most famous contender, trades point-like particles for tiny, vibrating strings, threads so infinitesimal that their oscillations dictate whether they manifest as quarks, photons, or even gravitons. These strings don't just dance in the familiar 3 dimensions, they require at least 10, with the extra ones curled into spaces too small for us to perceive. It's an elegant solution, mathematically harmonious enough to sidestep the infinities that plague other approaches. But critics argue its beauty comes at a cost. after decades, no experiment has detected these strings or their hidden dimensions. The theory's most tantalizing predictions, like microscopic black holes in particle colliders or cosmic imprints of string vibrations, remain frustratingly out of reach. Yet its allure persists, especially with ideas like holography, suggesting that our universe's 3D richness might be projected from a 2D boundary, like a cosmic mirage. Then there's loop quantum gravity, a rebel with a radically different approach. Instead of adding dimensions, it dissects space-time itself into a network of interwoven loops. Think of reality as an intricate chainmail, where each link represents the smallest possible unit of space. No smooth fabric, no singularities, just a dynamic quantum web where even the Big Bang might have been a big bounce from a prior universe. The theory's strength. It's grounded in testable predictions, like subtle modifications to the speed of light at ultra-high energies or quantum ripples in the cosmic microwave background. But it struggles to incorporate other fundamental forces, leaving some to wonder if it's a stepping stone rather than a final answer. Lesser known but equally daring is asymptotically safe gravity, which proposes that gravity's strength changes with energy scales, becoming safe from infinities at the quantum level. Picture a river smoothing out its own rapids as it flows. This self-tuning could avoid the need for extra dimensions or discrete space-time. Recent calculations show promise, but the theory remains in its infancy, lacking the experimental hooks of its rivals. The race to test these ideas is heating up. Gravitational wave detectors like LIGO and future observatories such as LISA could uncover anomalies in space-time's vibrations, hints of quantum foam or extra dimensions. Quantum simulators using ultra-cold atoms or entangled photons are recreating black hole dynamics in labs, probing how information might escape their grip. Even the cosmic microwave background might hide clues, with patterns that could reveal whether space-time is fundamentally pixelated or holographic. What makes this quest so electrifying isn't just the promise of a unified theory, it's the possibility that gravity and quantum mechanics aren't just incompatible, but incomplete. Like explorers mapping a continent, we've charted the coastlines but missed the inland mountains. The right theory won't just fill gaps, it could rewrite our understanding of existence, revealing whether space-time is a stage, a code, or something far stranger. Until then, the universe keeps its deepest secrets locked behind a door we're only now learning to knock on. The next decade in cosmology promises to be the most revolutionary in history, as groundbreaking new instruments come online, tools so powerful they could rewrite our understanding of the universe. At the forefront is the Vera Rubin Observatory, set to begin its legacy survey of space and time in 2025. Imagine mapping the entire southern sky every few nights, capturing tens of billions of galaxies in unprecedented detail. This isn't just more data. It's a cosmic microscope that could spot anomalies in galactic motions, revealing dark matter's hidden structure or even exotic particles beyond the standard model. And then there's the hunt for primordial black holes, relics from the universe's first second that might lurk unseen in these vast datasets. If found, they could solve multiple puzzles at once: the nature of dark matter, the seeds of galaxy formation, and clues about quantum gravity in the infant cosmos. Meanwhile, the Laser Interferometer Space Antenna, or LISA, will open an entirely new window on reality when it launches in the 2030s. While ground-based detectors like LIGO catch the high-pitched chirps of stellar mass black holes colliding, LISA million-kilometer-wide arms will sense the ultra-low frequency hum of supermassive black holes merging, events so colossal they warp space-time itself. But the real game changer, Lisa might detect gravitational waves from cosmic strings, hypothetical defects in space-time left over from the Big Bang. These vibrating threads, thinner than a proton but stretching across the universe, could be smoking gun evidence for string theory or exotic phase transitions in the early cosmos. And if we're extraordinarily lucky, Lisa could even spot echoes from before the Big Bang, ripples from a bouncing or cyclic universe that predated our own. Then there's the dark energy frontier. The Euclid spacecraft and the Nancy Grace Roman telescope will create 3D maps of the cosmos so precise they might catch dark energy in the act of changing strength over time. Is it truly a cosmological constant, as Einstein proposed, or a dynamic field that could one day rip atoms apart? The answer could determine the universe's ultimate fate. Meanwhile, next-generation neutrino detectors like DUNE and Hyper-Kamiok are hunting for cracks in the Standard Model, subtle differences between neutrinos and antineutrinos that might explain why matter dominates over antimatter. These ghostly particles, forged in supernova and the Big Bang itself, could be whispering secrets about quantum gravity or even extra dimensions curled up at unimaginably small scales. The wildest possibilities lie just beyond current reach. What if the James Webb Space Telescope's successors spot anomalies in the cosmic microwave background that point to a multiverse? Or if quantum computers simulate space-time so accurately they reveal it's an emergent property of entangled qubits? Every new tool brings the potential for paradigm-shifting surprises, perhaps evidence of higher dimensions from particle colliders, or strange signatures in action searches that rewrite dark matter's story. But here's the thrilling paradox of cosmology. The more we learn, the stranger the universe becomes. Each discovery peels back a layer only to expose deeper mysteries. Whether we're on the brink of unification or staring into an abyss of new questions, one thing's certain: the cosmos has never been more alive with possibility. The tools we're building today aren't just instruments, they're time machines letting us witness the universe's birth and maybe even glimpse the laws that transcend it. At the heart of cosmology lies a humbling truth: every equation describing black holes or quantum foam is also a mirror reflecting humanity's deepest existential puzzles. Consider the fine-tuning problem, the eerie precision with which the universe's constants, the strength of gravity, the mass of electrons aligned to permit galaxies, planets, and life itself. Tweak these values even slightly and stars wouldn't fuse carbon, molecules wouldn't bond, and the cosmos would be a barren void. Is this cosmic perfection mere luck or evidence of something deeper? Some scientists propose the multiverse as an answer, a vast ensemble of universes with random laws, making ours inevitable by sheer probability. Others see it as a hint of intentionality, a thread weaving through science and philosophy that even Einstein acknowledged when he marveled at the universe's comprehensibility. This quest spills into the very nature of reality. If space-time emerges from quantum entanglement, as cutting-edge theories suggest, does that mean consciousness, our ability to observe and measure, plays some role in shaping existence? The debate echoes the ancient philosophical divide between idealism and materialism, now dressed in the language of wave functions and holograms. Even the tools we use to probe the cosmos reveal a paradox. Mathematics, a human invention, describes the universe with uncanny accuracy, from planetary orbits to quantum spin. Is math discovered or invented? If the universe operates on mathematical rules, does that make it, as physicist Max Tegmark argues, a mathematical structure itself, a cosmic equation solving its own existence? The search for meaning extends beyond academia. Indigenous cosmologies have long framed the universe as an interconnected web, a perspective now resonating in modern quantum gravity theories where space-time is relational, defined by interactions rather than absolutes. Meanwhile, the simulation hypothesis that we might live in an advanced civilization's digital construct forces us to grapple with the nature of authenticity. If reality is information, does that diminish its wonder or amplify it? Perhaps cosmology's greatest gift is its refusal to let us settle for easy answers. Every discovery, from dark energy's push to quantum indeterminacy, chips away at our assumptions about causality, freedom, and our place in the grand scheme. The universe isn't just expanding, it's unfolding new layers of mystery, inviting us to ponder not just how it works, but why we're here to ask the question at all. In that sense, the study of space-time isn't just science, it's the most profound dialogue humanity has ever had with the unknown. As we stand on the edge of cosmic understanding, peering into the abyss of space-time's greatest mysteries, one truth becomes undeniable. The universe is far stranger, far more intricate than we ever dared imagine. From the mind-bending dance of entangled particles to the silent pull of dark matter's invisible hand, every discovery peels back another layer of reality, revealing questions we didn't even know to ask. Think about that for a moment. Black holes, those cosmic paradoxes where time itself grinds to a halt, might be gateways to other dimensions. The vacuum of empty space, once thought to be nothingness, seethes with quantum energy so potent it could rip the cosmos apart. And the very fabric of space-time, the stage upon which existence plays out, might be nothing more than a holographic projection from the edges of reality. What makes this journey so exhilarating isn't just the answers we've found, it's the sheer audacity of the questions still unanswered. Why does the universe have a speed limit? What breathes fire into the equations of physics, transforming abstract math into planets, stars, and conscious minds? The more we learn, the more we realize how much lies beyond our grasp, waiting in the shadows of the unknown. Yet this isn't a cause for frustration, it's an invitation. Every generation has its pioneers, from Galileo pointing his telescope at Jupiter's moons to the team behind the Event Horizon Telescope capturing a black hole's shadow. Today, that torch passes to all of us, whether we're professional scientists or simply stargazers lying on a backyard blanket, tracing constellations with our fingertips. So where do we go from here? The next great breakthrough might come from a lab buried deep underground, where detectors hunt for dark matter's whisper. It could emerge from a quantum computer simulating the birth of space-time itself. Or perhaps it's already hiding in plain sight, tucked away in data from a telescope or encoded in the faintest ripple of a gravitational wave. One thing's certain, the cosmos isn't done surprising us, and that's why we keep looking, keep questioning, keep daring to imagine the unimaginable. Before you go, let's make this conversation bigger. Drop your wildest cosmic theories in the comments. Do you think we'll crack the mystery of dark energy in our lifetime? Could wormholes really be out there waiting to be found? And if you enjoyed this dive into the universe's deepest secrets, don't forget to like and subscribe for more mind-expanding adventures. Until next time, keep your eyes on the skies and your mind open to the infinite possibilities. The universe is calling. Are you